Welcome to Expressions and Equations. Today, we're looking at how to solve real-world mathematical problems that have two unknown variables. When a situation has two missing pieces of information, knowing just one fact isn't going to be enough to find a single specific answer. To accurately model what's happening, you need to set up two separate linear equations. This allows you to track two independent rules or constraints at the exact same time. Let's see this in action with a ticket sale. Imagine adult tickets cost $8 and student tickets cost $5. A show sells 30 tickets in total, making exactly $201. First, we define our variables. Let A be adult tickets and S be student tickets. Then, we write our two equations, one for the total quantity, A plus S equals 30, and one for the total monetary value, 8A plus 5S equals 201. To solve this, we can isolate one variable. If we take our quantity equation and subtract A from both sides, we find that the number of student tickets equals 30 minus the number of adult tickets. Now we can take that expression, 30 minus A, and substitute it in place of S in our second, more complex value equation. From here, we multiply the 5 through the parentheses to get 150 minus 5A. Combine the A terms, subtract 150 from both sides, and divide by 3. We get 17 adult tickets. Plug that 17 back into our first equation, and we find there are 13 student tickets. A real-world system uses two equations to track two quantities at once. 17 adults and 13 students is the exact combination that satisfies both the physical headcount constraint and the financial constraint. We can also use systems to compare two different rates. Suppose we want to find out when two recurring phone data plans cost the exact same amount. Plan A costs $20 up front, plus $3 per gigabyte. Plan B costs $35, plus $1.50 per gigabyte. We can write these cost rules using G for gigabytes. To find the exact moment the two plans cost the same, we simply set the two equations equal to each other. We group our variables on one side and our numbers on the other. Subtracting 1.5G from both sides, and then subtracting 20 from both sides, leaves us with 1.5G equals 15. Divide by 1.5, and we get G equals 10. The plans cost the exact same amount at 10 gigabytes. Setting two linear models equal to each other locates the exact input where both models produce identical outputs. Mixture problems combine these mechanics. A store mixes peanuts that cost $4 a pound with cashews that cost $7 a pound. They want to create a 10-pound mix worth exactly $55. Just like our ticket problem, we write an equation for the total physical pounds, P plus C equals 10. Then we write one for the total monetary value. Take a moment to think. Based on our earlier ticket sale, what expression do we substitute for P in our value equation? Since P plus C equals 10, we isolate the variable to get P equals 10 minus C. We drop that expression right into the value equation. Distributing the 4 gives us 40 minus 4C. Combining that with the 7C leaves 3C. Subtract 40 from both sides to get 3C equals 15, meaning C equals 5. If the total mix is 10 pounds, the peanuts must be 5 pounds too. Mixture problems always rely on this dual structure, one equation to track the physical amount and another to track the intrinsic value. Whether working with ticket sales, data plans, or trail mix, the strategy remains consistent. Define your variables, write your two equations, and substitute to solve. Mastering these steps gives you a reliable tool for tracking multiple constraints. This refines your ability to work with systems and sets a strong foundation for the modeling you will do in high school algebra. Look at your own life today. What is a situation you encounter that involves two variables and two constraints?